start this recording, that would be catastrophic. Well, not shrinking, just migrating.
Sorry.
Migrating down into the virtual. No, I think I've had a class where well, there weren't that many in it. I think there was 12 people or something, but 2 people showed up. I was like, okay, gather around, guys. All right. So, today I decided we got to do our stats because remember we're going to do that little bit of statistics. So we bit off a fair chunk of the background. The rest of the background I'll kind of introduce as we need it. Okay, and so of course I'm not going to leave you hanging. And so we'll just kind of bake it in as we go. But there was a little bit of stats that we're going to do, and depending on what kind of stream you go down, still funny, then you might take stats probably with me or, well, someone else maybe, but I know a group of you take stats, and so we're not going to go very deep, but just so you all have kind of the core understanding. And remember, stats my jam, so should be pretty fun. No, it's just pretty basic today, but that's all right. Oh yeah, as a little quick review, well, we finished the skills assessment, right, and then we started talking about sig figs. We had the sig fig, he said, she said. I got to the bottom of it. Nobody cares. So basically, they were kind of like, oh, we thought you cared about that stuff. And I'm like, no, I thought you cared about that stuff. No. So I only talked to Frank and Allison for what they do, right? 3 sig figs, but Allison was kind of like, well, they need to know, the rules and stuff, and how it works, but kind of use good judgment. Okay, fair enough. And then I have not talked to Dave, and of course, it kind of, Allison told me that Dave is a little bit different, so whatever Dave says, do with Dave. But for me, as long as you know the rules and you kind of are aware that there are sig fig rules, that's fine. Typically, I'll just kind of tell you, or if it doesn't matter, then I don't care, right? And so, because what I was kind of trying to say to Allison and Frank is that in math, all digits and all figures are significant. We don't lob them off, they're all significant. And so in this course, we won't focus too much on sig figs. But you are expected to know the rules. To know the rules and how to apply them. So basically just roll with the punches. But this is a safe space. A sig fig safe space. Okay? And so, of course, if I ask you a question about sig figs, then you should probably know how to do it. But besides that, no. Okay. Any questions about that? Was there anything else that we kind of, I feel like that's where we ended last day. It's kind of a big question mark. Yeah. But anyways, so Frank just says 3 sig figs. I said, oh, can I do that? said, sure. And then I was like, well, there are some scenarios where that doesn't really work, right, if we want to get precise. And then Allison said, well, it kind of depends. Okay, so. That is good. That is good. That's always the goal, right? When working with colleagues like that. Do whatever you can to make them feel guilty. Okay, so today we're going to do just kind of touch on statistics. Nothing major, nothing crazy. Has anyone taken stats before? Yeah, nice, cool.
Yeah, I have.
Hey, nice. Is it you actually has the mic on?
Yeah.
Do you mind turning it off?
Yeah, no problem.
Thanks. It's like the radio here.
Hi, Ash.
You can't answer now. Thank you, that's great. Okay, so we're gonna do some statistics. And so first, because a lot of you haven't taken any statistics, let's talk just briefly about what it is. We're not gonna do anything crazy. We're gonna talk about measures of center and spread essentially today. And then Allison asked me to just touch on confidence intervals, which will make more sense when we get there. But that's about it. Okay, just to be aware of these terms and then just kind of carry them on to your other courses. Okay? And so what is statistics? Statistics is essentially just when we're using sample information to learn about a whole population, right? And so a population is just whatever you want to study, right? So whoever satisfies that criteria or whatever satisfies that criteria would be the population. You take a subset, that's your sample. I think these are terms that we kind of use in everyday life, but it's when we're using sample information to learn about a population. And I'll underline sample and population because those are important. Okay. So a population is just everything that satisfies the characteristics we're interested in, right? And so for you guys, you might be interested in some body of water, I would imagine. I don't know, right? That seems reasonable and vague enough, right? So some body of water, that would be your population. You understand that you cannot collect information from the entire body of water, right? That's impossible. And so you would take samples at different places in this lake or whatever, right? And then do measurements there. And then you can do calculations on that sample to learn about the whole lake, let's say. So everything that satisfies the criteria of your study. So often I kind of talk about, well, okay, so the college wants to survey students, and so kind of silly because they definitely could ask every student at the college, but it would just be very time consuming and very costly, right? And so they would just take a sample of students, right? And so we've got the population of students and you take a sample. So the sample is a randomly selected And it's important that it's random, right? Or you make every attempt to make it random. So a randomly selected sample, subset, shouldn't use the word in the definition. A randomly selected subset of the population. So this relationship between a population and a sample, that's the heart of statistics, is when we take, okay, we've got sample information, so we can calculate things like averages and standard deviations on the sample, and then what does that mean for the whole population, right? Using that sample average, what do we think the population average might be? And so kind of the main thing that we do is we talk about measures of center, okay? Because these measures of center are often used for predicting things or forecasting, right? And so they're kind of our best guess, right? So our sample average. But in general, we've got measures of center. Are often used as our best guess. I'll put that kind of in quotes. It's not really. Or a forecast / prediction. So usually that's the role of a measure of center, right? And so we all know what an average is, right? Average height, average grade, average whatever, right? And we all know how to calculate an average, right? Add up all your things, divide them by however many there were, right? And that's your average. And so we're pretty comfortable using that as a prediction, for example, right? To say, well, what was the average grade in that class, for example? And then you can kind of figure out, okay, where would I fall if I took that same class, right? That kind of thing. And so we're going to talk about 3 different measures of center. These are kind of the most common ones. I usually only focus on the mean and the median, but we'll start with the mean. The mean is the average, okay? And so whenever you say average, you actually mean the mean, okay? And so that's just when we add up all our values and divide by the number of values. This is where I'm going to take the opportunity to potentially introduce sigma notation. Have you guys seen sigma notation? No, not really. Okay. But so the mean is denoted by X bar typically, but anything with a bar over it is an average. And so this is just the average of X. Anything with a bar over it is the average. I usually use this. It's your average smiley face. So anything with a bar over it, it just says, oh, here's the average of whatever's underneath. Okay? So we've got a little bit of notation, not that crazy, but X bar, the formula for X bar, now we already said, so we already know how to calculate this. It's just making the connection between the notation and what we are doing. We said that, okay, well, we're gonna add up all our things, right? You wanna take the average height of 10 people, for example, right? You record their heights, right? And then you add them up. And so that's what this capital sigma is. So capital sigma. In stats, we love the Greek letters, but sigma is just in math. And it just says, add up all the things inside here. All right, so add up all your x's is what this is saying. And divide by n. Lowercase n is always your sample size. So sigma x says add up all the x's. Any questions?
Oh no, I just drawing the sigmas.
Oh, yeah.
You want it to go backwards from every letter?
It is actually, yeah. And I'm doing a crappy job. Should be more kind of strict, I guess. I'm just sloppy. Oh, slop. And I'm skipping some things because technically on the sigma, typically you say I equals 1 to n, and then you have x subscript I. Don't be scared if you see that. You can just ignore the i's typically. I'm not going to do that, right? But it's gone. No. It just says from I equals 1 to n. So from the first data point to the nth data point, it's just leaving it open to any sample size. Because remember, n is the sample size. So it's just saying, take all your data points, add them up, and divide by n, the sample size. Okay. Cool. I know that's a lot of new stuff, but hopefully not too bad yet. Okay. So one thing to keep in mind about the mean, or the average, if you're using it, is you would want to spend a little bit of time to look at the distribution of your data, okay? Which, of course, if you keep going, then I'll show you how, but not in this course, okay? But we need to look at the distribution of our data. Because the mean is not robust to outliers. And you might have heard of outliers before, right? Because they're just extreme values. An outlier is an extreme data point. Okay. And so the mean is always pulled towards, it's pulled in the direction of these extreme values. Okay? And so what it means by not robust is the mean is pulled towards extreme values. Oops. So if you graph your data and the distribution ends up looking something like this, right? This is a normal, this is what we call a normal distribution. It's actually the name, normal, or Gaussian if you prefer.
Okay.
Normal's good, right? They look the same though. But so this is a normal distribution, kind of this bell-shaped curve. And so because there are no extreme outliers and there's no direction or no tail for the mean to be pulled in, the mean is a good measure of center in the middle, right? If we have something like this, so we've got this long tail and then we've got this bulb here. This is a skewed distribution. And so what this long tail is saying is that there's just a few values out here that we need to look at, right? So we've got these extreme values down here. Oh, and I think there's a page break. That's not very helpful. They added that as a new feature this year. It's really helpful. Because otherwise when I scroll through my notes, it just chopped them randomly. But now I have to pay attention. So these, I'll just say, are outliers. So a good measure of center here would be kind of in the bulb of things, right? That would be the center, right? But what happens is that the mean kind of gets pulled down towards these outliers, and so it's not a very good measure of center anymore. Not a good measure of center. I'll add to the top one here. When we have this beautiful normal distribution, and lucky for us, the normal distribution happens a lot. Right? And so even in things that you don't really think are going to have a normal distribution, quite often they do. Okay. So here, this is a good measure of center. Okay. All right. And we'll do calculations of all these things, but I'll introduce them all first and then we'll do some examples. Okay. So that's the mean. So if we want a robust measure of center, what we go for is the median. So the median is, if we arrange all our data points from smallest to largest, the median is the middle one, right? And so it doesn't care what the values are, like the mean does. The mean adds them all up and divides them, right? So the values of these data points matters, right? But for the median, it doesn't care, right? If the first value is 1 or 100 or whatever, right? And so the median is a robust measure of center. And so the median, I guess this is our second center. Is that what I did? 1, 2, yeah. So the median is the central value first sort your data from smallest to largest. Then I use my my patented boop, boop, boop method. And I just kind of boop my way into the middle. And that's how I find my median. Of course, there are formulas, but I find them kind of misleading because they only help you find the position. And so then you still have to count in to find the actual value. And so I don't use that. There are, of course, like I said, there's formulas for everything. But to find the median, the easiest thing I find is just sort your data from smallest to largest. And then, because we'll never have huge data sets, or if we do, we'll use Excel, and there's just a median function, and it can just find the median, right? And so, but for by hand work, we just sort our data, and we boop our way in. Easy enough. Yeah. And then, so first sort your data from smallest to largest, then boop, 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 3 boops. I don't know how else to say it. Your way in from both sides. To find the central value. Okay. As a note, if you happen to land on 2 values at the same time, you take the average of those. That's confusing, right? Because we're finding the mean, and then we're to find the median, but that's just how it is. So if we land on 2 values in the middle, we take the mean, right, the average of them as our median. So, what's nice, like we said, is that the median is robust to outliers. Okay? And so the median is robust to outliers. Making it a useful center or a measure of center, right? Even for skewed distributions. Making it a useful measure of center even for skewed distributions. Skewed distributions. If we have a normal distribution, right, then, so if we have a normal distribution like this, then we said, okay, well, here's the mean. It's in the middle where we expect it to be. That's good. And the median, remember, we just count in, blah, 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 blah. If we have a normal distribution, the mean and the median are going to be approximately the same. The mean, I'll say roughly equal to, because there's a little bit of flexibility, the median. Yeah. If we have a skewed distribution, I guess I should label this again. This is a normal distribution. If we have a skewed distribution, let's skew it the other way this time. Nice. Only my axis was a little off. It's all right. So then here, now we have a skewed distribution. And we said, okay, well, the mean gets pulled in the direction of the tail, right? And that's what it means to be not robust. And so we've got the mean down here somewhere. But the median is robust. And so it'll just hang tight here and it'll just be at the center of most of the data. So if you only know the mean and the median, right, without looking at the distribution, you could tell me if it's skewed or if it's normal just looking at those values, or you could have a pretty solid guess at whether it looks normal or skewed. Right. Not that that's something I would expect of you, but just to kind of keep those things in mind when you're looking at summary data. Yeah. So, what else did I want to say about the median? Okay, so we use the median as our measure of center if we have skewed data. Okay? We can always use it, right? Because like we saw here, if we have a normal distribution, then the mean and the median are essentially the same. So the median is always a good option. Right? The reason that we prefer the mean is because there's so much kind of calculating power behind the mean. And so there's a lot of tests that have been developed, and just kind of, there's a lot of things that we can do with the mean that we can't do with the median. Okay? And so we're always hoping that we have a normal distribution so that we can make use of these tests. Okay. The median is always a good measure of center. But if we have a normal distribution, we can use the mean as our measure of center. And the mean has more powerful analytical tools. I don't know, just has more powerful, I don't know, yeah, analytics. I said it. Tried not to.
And why does it have more power?
It's just, well, I think it's what people like to use. And it helps that there is a strict formula for using it. And so we're able to manipulate that in a lot of ways. Whereas the median, we have a formula for finding the position, but it's not really like a mathy thing. And so I think that's why they've been able to develop all these tools around the mean, and then the median, it's kind of like, well, yeah, sure, here's the median.
It's like the mean is like a definitive value, like
Right.
summarizes the data, whereas like
Totally.
the median is just like a nice way to find
The center.
Yeah.
Totally, exactly. Yeah, and so whenever we can use the mean, that's what we want. Right. Oh yeah, any questions? Did I write too fast, too sloppy, too small, too big? Good. Okay, then finally, the third one, which I'm in stats and I don't even mention it anymore, is the mode, but I guess I should. The mode isn't that impressive. It's just the value that occurs most frequently in your data set. Okay, and so it's the value that occurs most frequently in your data set. Often it's not even that good of a measure of center, right? But I mean, I guess it's okay. But it's not that impressive. So you look at your data, usually if you're finding the mean, the median, and the mode, then you've got your data sorted from finding the median, and then it's easy to figure out which value was the most common value. Right? But yeah, so there are your three measures of center, two heavy hitters, the mean and the median, and then the little mode kind of trailing behind. And there can be more than one mode. In the case of multiple modes, leaving room for even more than we say our data is multimodal. Or in the case of two nodes, or two modes, we say bimodal. So it's definitely an option. Might look something like, ooh, bimodal. Yeah. Bimodal distribution. You could, but here I'm going to go ahead and assume that we have a large data set, right? And so then if we have a bimodal distribution for small data sets, yeah, that's what would happen, right? You would have kind of like this. But for large data sets, then it just kind of smooths out, and then there's like, even as you're building up, there's not one that's as common as the other one, right? They're kind of building on each other. Okay. Okay, so those are our centers. Now let's go on to our measures of spread. And so a big concern in statistics is to capture variability, right? Because what we know is, okay, so from a population, we took a sample, right? And so we've got this sample information, but we know the sample isn't exactly like the population. And so there's variation between the sample and the population. And so we're trying to capture that variability. And so that's why we need these measures of spread to know the variation. Okay. Measures of spread. Since we know our sample will, and I'll say vary from our population, even if you think about collecting one sample and then you collect another sample, you don't actually expect even those averages to be the same, right? You're expecting a little variability from sample to sample, right? So since we know our sample will vary from our population and even vary from sample to sample, our main concern in statistics, is capturing variability. Or at least have a pretty good idea of what the variability might be, right? Or at least have a good idea about what the variability might be. And so that's what these measures of spread are going to try to communicate. And so our measures of spread will help communicate, communicate the variability in our data. So the first thing that we're going to look at, or the first measure of spread, is the mean absolute distance. Or the MAD. Okay. So the mean absolute distance, well, everything is in there in the name, right? The mean is the average, right? Absolute, have you guys heard of absolute values? Do you guys know absolute values? Essentially where you drop the negative, so it becomes a distance instead, right? And so a distance is an absolute value. And just take, for example, right, 1 is 1 unit away from 2, but 3 is also 1 unit away from 2, right? So the distance doesn't matter. And so the distance is the absolute value, and it's in there twice. So mean absolute distance. And so what we're going to be looking at is how far, right, what distance is each data point from the mean, right? Oh. And then we take the average of that. How embarrassing. And so the MAD is the average distance of the points from the mean. Huh? The MAD, if we're going to calculate it, I'm going to give you the formula and then we'll kind of talk it out like we did the other one. But we've got your favorite sigma again. Sigma. So we're going to, right, because we're taking the average distance from the mean. And so, of course, we have to add up the distances from the mean. And so that sigma is no surprise, right? But then we're going to take the absolute value of x minus x bar. If you want, you can put a little subscript I down there, but I'm going to drop it because it's implied. Like I said, don't be scared when you see the I's on there. Typically, you can just ignore them. Sometimes. Over the sample size. Okay. These vertical bars here, I'll do a different color maybe. The absolute value essentially drop the negative, drop the negative, have a negative number, and so it just turns it positive. Okay. And then we add those all up and divide by however many data points we had. And so x minus x bar, right, that's that term inside the absolute value. If you think about that, that's just each data point, how far is it from the mean, right? Because remember, this is the mean, and this is each data point. So you have to do it to each of them individually. Right. Then you drop whatever negatives you get, and then you add them up and divide by n. But this distance from your data points to the mean that's your error, right? Because you've got your mean, and then you've got your actual observed data points. And so this is your error. Usually denoted by an epsilon, but nah, we can just call it the error. But if you want. No. So it takes each of these error terms, right? How far off is each data point from the mean, right? And then we look at those as distances by taking the absolute value, and then we add those up and divide by however many data points we had. Okay? And that's the MAD. Okay? Any questions about that one? Okay. Number 2. Our second measure of spread is the variance. Okay? And the variance does, it's kind of an amped up version of the MAD. Okay? And it's a more common measure of spread. The variance, I tried to find like a definition of it. It's and it's not very helpful, it's the sum of the squared error terms divided by n-1. It's just the formula, so that's not very helpful. But again, it's looking at these error terms, right? The distances from the mean, but then instead of taking the absolute value, we're gonna square those values. Remember, squaring even a negative number makes it positive. So again, it's going through that procedure of squaring things and making it positive, then adding them up and dividing by n-1, and that's just a little hang up thing. It's not, could be n, but it's to try to be as much like the population as possible. It's not important. Okay. And so the variance, I don't really have a formula for it or a definition for it, so I'll just give you the formula. Now we're pretty good at these sigmas. And then in brackets, we've got x minus x bar. Notice that that's just the error term. And then we have to square all those. Okay. And then we divide by n-1. So here, what this is saying is it's saying, okay, well, find each of the error terms, right? So each data point is going to have an error term, right? Square each of those error terms, and then add them up, and then divide by n-1. And so because we're squaring things, right? The variance is not as robust as the MAD. Okay? Again, so the variance and you'll see the standard deviation, which is just like the variance's little brother, because it's just the square root of the variance. They go together with the mean, right? So as long as we have kind of a normal distribution, then we can use the variance and the standard deviation and the mean. But if you need something more robust, then you could probably use the MAD. But again, just like the median, even though it's more robust, there's not as many tools that we can use. Okay, and so the MAD is more robust, robust than the variance. And it's because we're squaring things, but I'm not sure that's important for you guys to know. You can just remember that the mat is more robust than the variance. And I'll put in brackets here and standard deviation. I guess I should have introduced it first before I gave you that tidbit. However, like the mean, the variance is more powerful as long as we have a normal distribution. So I guess I should give you the standard deviation. Oops. Standard deviation is the square root of the variance. Okay. And usually we just denote it by a lowercase s. Is the square root of the sum of the x minus x bars squared over n minus 1. The variance we can usually write as s squared, right? We can usually denote the variance as s squared, just as shorthand if you want to. Right. So s is the standard deviation, and if we square that, we get the variance. Right. And so that's why I say they're basically the same. You could use them interchangeably, right? Or at least, I don't know. As long as you have the variance, you can find the standard deviation and vice versa.
Why is like we do this is something obvious, but like s, like the square root of s squared is that. So like how are they usefully different? Like what's the difference?
Yeah, they're not different.
It's like the exact same value.
Yeah, they're the same. One's just the square of the other, right? And so, yeah, if you take the square root, you can get down, right? And so we get s is the square root of s squared. That's what you're saying, right? And that's true.
Is there value to having different terms, or is it just kind of what's out there?
No, it kind of depends more on your field. So in stats, like lower level stats, we like to use the standard deviation. Upper level stats, you end up using the variance more for whatever reason. And it just depends kind of where you're going. And I don't know what you guys use, or if any, really. Obviously, if you keep going with stats for me, we'll use the standard deviation, but just to be aware that they're, that's why I call the standard deviation the variance's little brother. So it's just take the square root. Okay. So, all right. So we've got 3 measures of center, 3 measures of spread. How about we go through and do some calculations? Any questions though before we do? Yeah. So let's do an example. we're gonna have data set number 1, 6, 7, 3, 2, 8, 2, 8, and data set number 2, 6, 5, 4, 5, 6, 4, 5. Just double check that they both have sample size of 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Phew, didn't miss any. So they have the same sample size. And I think intuitively we're already pretty good at seeing things like variability, right? And so if I asked you, now these are pretty similar, but if I asked you to pick which one had more variation in it, right? Which data set has more variation than the other? I'm guessing you'd go for data set number 1, right? It's kind of a wider spread. And so already we know this thing about variability, bless you. Right, and so we know how to see it and we know kind of what it is, right? And so we're gonna go through and we're gonna calculate all 3 measures of center and all 3 measures of spread for each of these, and we can do like a comparison. Okay. So just make a note here. We see data set number 1 has more variability than data set number 2. Let's so I guess part A, find the mean of each data set. So I'll get fancy and use some notation, but really for this course, since it's not a stats course, however you find the average is fine for me. But I'm gonna say X bar, and I'll put a little subscript 1 just to keep track of data set 1, data set 2. Okay. Is the sum of all my x's over n, which is going to be 6 plus 7 plus 3 plus 2 plus 8 plus 2 plus 8, all over 7. See if I find any quirks using this calculator. Oops. It's nice that it has the delete button. I've got some calculators that don't have a delete. Hey, 6 plus 7 plus 3 plus 2. No, one of these values was supposed to be, let's make this last 8 a 7 instead. Don't worry, it'll make your math much nicer. How about that? Yeah. $35 over 7 is much nicer. Oh. Hopefully I didn't forget to change other one too. Okay, good. We all got an average of 5 now that I changed the last value. Good. How about the mean for data set number 2? It is 6 plus 5 plus 4 plus 5 plus 6 plus 4 plus 5. 1, 2, 3, 4. Good. Which again should be 35 over 7, which is 5. Obviously, I'm showing way more work than you have to, but the more the merrier, right? Okay. So far, we've got the same mean, right, for each of these. By design, of course. Okay. So, what if we go ahead and find the median of each of these? Okay, so how about we'll do the first one together, and then I'll give you a little bit of time to work on the second one. And so part B, I guess. Find the median, plural, find the medians. Data set number 1 sorted. I have 2 2s, 2, 2. I've got a 3, and then I've got a 6 and a 7, another 7 and an 8, right? Did I muck it up? Wait, 1. That's good. With the change? 1, 2, 3, 4, 5, 6, 7. It's always a good idea to make sure that you still have 7, so you didn't lose 1. And so now, like I said, this is where once you're sorted, it only works if you're sorted, okay? But this is where I just use my boop, boop, boop. And so I just kind of boop, 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 boop. And then that's my median. Okay. The formula that I was talking about, it would tell you 4, but it would just mean the 4th position. So 1, 2, 3, 4. So that's why, I mean, you still have to count in, and so it kind of doesn't save you any time. And so here, I'll kind of show how we did it. Boop, 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 boop. Woo. So the median here is 6.
If you had 8 points, would it just be the 2?
Yeah, so then you would land on 2, right? And then you would take the average of those 2.
Oh, so then you would find the mean of those 2 points.
Yeah, so for example, say we had the same data set, 2, 2, 3, 6, 7, 7, 8, 8, right? Adding on that last one. So then we would kind of boop, 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 boop. And so we'd land on these 2. So how you show it is you would circle the 2, and then you draw a line through here, and you would say the median is 6 plus 7 divided by 2. So the median is 6.5. I should clarify what I changed here. For example, with 8 data points. I'll get started on the second data set, but if you go ahead and try to find the median of the second data set, that would be good. Number 2 sorted. Change that while I'm seeing. Remembering. Sorted, we have 4, 4. 1, 2, 3, 5s. 1, 2, 3. And 6 and 6. 1, 2, 3, 4, 5, 6, 7. Yeah. Kind of boring data points, I know, but it's just to show you what to do. All right, so you boop, boop, boop your way in, and hopefully you land on 5. Boop, 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 boop. So the median is 5. Okay. So we know the mean is 5, right? And so what can we say about the distribution? Now this is just kind of taking it to another level of the first data set. Here we kind of expect it to, these are small data sets, so it doesn't really necessarily translate. But given a scenario where you have a mean of 5 and a median of 6, then you would have something like this. So data set 1, number 1, might look something like, oops. Like this, right, where you've got a bit of skew here because the median was at 6 and the mean was at 5. Right? And remember, the mean gets pulled in the direction of the tail. And so now you have a pretty good idea of what this distribution might look like. And data set number 2 might look something like this, because we know we have the same mean and median. So the mean equals the median, which equals 5. So then we would be expecting to see something like a normal distribution. And so a lot of the time, and even throughout this whole math course, it's going to be more about what do you expect to see, what do you expect to happen, right? And so kind of knowing enough to know what to expect, and then you can get down to the nitty-gritty and kind of calculate it out and see. But knowing what to expect is a really important skill. All right, so we've calculated the mean, we've calculated the median. We can go ahead and calculate the modes. Find the modes. Data set number 1, if I just steal my sorted data here, 2, 2, 3, 6. 2, 2, 3, 6, 7, 7, 8. 1, 2, 3, 4, 5, 6, 7. Good. So I've got 2 2s and 2 7s. So data set number 1 is bimodal at 2 and 7. Data set number 2 sorted was, oops, 44, no. 4, 4, 3 5s, 1, 2, 3, and then 2 6s. 1, 2, 3, 4, 5, 6, 7. Good. And so we can see that we only have one mode. You could say unimodal if you want, but one mode at 5. Which backs up what we think it might look like, right? Because now we're saying, okay, well, we've got one mode at 5, where the median is, where the mean is, right? And so it very likely looks like that. Data set number 1 looks probably a little different than what we thought. Looks like it might have a little bump in the bottom and then another bump at the top, which kind of shifts your mean around. Right? So then you should definitely use the median as your measure of center, right? Because it's more robust.
So for that one, is it just a coincidence that radians at 6, so well with 5, triangle includes 7, so it's shifted over 1. Is it coincidence like that? That's a plus and minus.
Do you mean data set number 1
Yeah.
or 2?
Number 1, instead of being like median is 5 and median is 6.
I think the problem is that we're looking at a very small data sets, and so everything kind of matters. And so we're looking at these, but it's really only going to matter once we have larger data sets. And so then if you're seeing shifts like that, it's not a coincidence. But here it's probably just my imagination not being very good. Okay. All right. So find the MADs. So we can do the first one together, and because I don't deal with the MADs so much, and I don't know, I just like watching Sal Khan work. I was curious to see how he approached it, and he actually had a really good kind of starting graph to show it off. So I'm going to steal that shamelessly and show you how Sal Khan does it. You guys know Sal Khan, right? Khan Academy? Okay, good. Anyway, so what he does is he says, okay, well, let's look at the number line here. of all our data sets. So data set number 1. And I'll just refresh what the formula was. Since I have a little bit of room here, doesn't really matter. Is the sum of the absolute value of x minus x bar over n. So data set number 1, once we were sorted, we had from 2 to 8, right? And so what I'm going to do is I'm going to make a number line from 2, 3, 4, 5, 6, 7, 8. And this is to visualize the distribution, kind of a quick visualization. And so we had 2 values at 2. So I'll just put those here above 2. 2, 2, 3, 6. So a value at 3, a value at 6. And notice that I'm trying to put them all on the same level, right? So there's like first dot, second dot. And then 7 and 7. And then 1 at 8. So each of these dots are our data points, right? And so those are our x's. And so what we're going to do is we're going to draw on our x bar here. X bar is 5, right? That's our mean. And what we want to do is we want to find the distances of all these points from the mean, right? And we do that by taking the absolute value in the mathy way, right? But if you're just looking at these, then you can say, okay, well, I know 3 is 2 away from 5, right? And so even though it's 2 below 5, right, that's where the negative comes in, below. But if you just are talking distances, right, you drop that negative. And so you're already doing that. And so you could calculate the MAD without using the formula, right, by just taking, okay, the average distance from the mean. That's what the MAD is. Right? And so you find each of these distances. And so from this one, we've got a distance of 2. Here we've got a distance of 3. And again, we've got a distance of 3. Moving over to the right-hand side, we've got a distance of 1. We've got 2 distances of 2. And then finally a distance of 3, which I'm going to squeeze in where? Here. Okay. These distances are our error, right? That's basically how wrong our points are from the average, or rather our averages from our points. Right. And so we've got the sum. If we do it properly, the MAD is the sum of the absolute value of x minus x bar over n, which is going to be the absolute value of, now I'm just showing mathematically what we were able to do so easily by just drawing those arrows and figuring out those distances. But what we're doing is we're taking the absolute value of first 3 minus 5 plus the absolute value of 2 minus 5 plus the absolute value of 2 minus 5 plus the absolute value of 6 minus 5 plus the absolute value of 7 minus 5 plus the absolute value of 7 minus 5 keeps glitching. There's no ink in here. I don't know why I shook it. Oh. Room for one last one. 8 minus 5. All divided by 7 data points. Notice how I kind of bump in my pluses when I have to move to the next line because I ran out of room. I just kind of bump it in a little bit so it's not as messy, and then each time I kind of bump it in, leaving myself less room on each line, but that's all right. And the absolute value of 3 minus 5 is 2. Plus the absolute value of 2 minus 5 is 3. Plus 3 plus 1 plus 2 plus 2 plus 3. Right? And those are just the distances that we have here. Right? So now we're at the same part where we left off with those distances. Right? And so if I said, okay, now take the average of those distances, what would you do? You'd probably say 3 plus 3 plus 2 plus 1 plus 2 plus 2 plus 3. Add them up, divide them by 7, right? Because there were 7 numbers. And that's what we're going to do. Add them up and divide them by 7. So I get 2 plus 3 plus 3 plus 1 plus 2 plus 2 plus 3. 16 divided by 7. So what you guys got? Or did I miss a term? Did you guys get 16? So it's either 2 2/7, which your calculator kindly gives to you, or 2.2857148604286. Sorry. Ish. Yeah.
I've noticed a couple times we'll go through our calculations and ending in fraction. Do you want us ending in fraction, or do you want us going in other?
To me, 16 out of 7, you're done, right? And so unless you're using it later on and you don't want to work in fractions, then you can convert it to a decimal. But I mean, the math person in me loves fractions because they're precise, right? And so that is the most accurate answer. And so converting it to the decimal, we lose a little bit of precision, but it's easier to work with. And so that's why I kind of convert to decimals. And it's easier to think about 2.28 rather than 16 over 7 or 2 2/7, whichever one you get to. And so, yeah, leave it as a fraction if you want to. Like, if that's the end of the problem, don't worry about it, right? 16 over 7, you don't even have to simplify it, it's fine. But yeah, so it kind of depends on the scenario. And of course, in a test situation, you can just ask me if it's not clear which one I mean. But yeah, so yeah, leave it as precise as you can if you want to. Okay, so the MAD, we've got a pretty good handle on just kind of intuitively, right? Because we're thinking, okay, well, I want the distance from the mean. So as soon as you learn that, okay, it's the average distance from the mean, then you can kind of figure your way to that, right? Let's do the second data set number 2. Now you can use the little timeline that we did, drawing the distances, that's totally fine. I'm just gonna skip straight to the equation because that's what I like. But the MAD is the sum of the absolute value of x minus x bar over n. I know they're way up here. Woo. 4, 4, 5, 5, 5, 6, 6. Okay. 4 minus, and the mean was 5 for both of these, right? So I don't have to scroll around. Plus 4 minus 5. Plus, this is going to be a lot of writing for a bunch of zeros, right? 5 minus 5 plus 5 minus 5. Oops, 5 plus 5. Oh, that'll be different. Plus, and then I think 2, 1, 2, 3, 4, 5. Yeah. Divided by 7. 1 plus 1 plus 0 plus 0 plus 0 plus 1 plus 1. 1, 2, 3, 4. Point 57142. 142 85714.
So,
Less.
in general, like the lower the MAD, the more consistent the data point. So it's like,
Exactly.
is it better?
It's less variability,
Yeah.
right? So there's less variation in there. And so, yeah, so exactly what you said. So we already suspected data set number 2 had less variability, and that's what we're seeing in this low MAD, right? So go ahead and calculate the variance and also the standard deviation at home, and then we'll do those together, of course, on Thursday, but otherwise, see you then. Yeah. Bye, guys.